And I'm sitting there smiling. This guy has never applied for visa from a developing country. He'll never say that. So that is not like there's a balance.
Mitigation has two aspects. One, she's getting ready. We know nothing about the impacts of trying to sequester farming. That has to be done very carefully. Secondly, the basic adaptation techniques of not cutting down forests or using agroforestry and other things are being ignored in a rush to develop some manageable solutions. So I think mitigation that has to be done very carefully.
Okay, basically I'll sort of pick up where Laurent left off. So basically what he's talked about and what happens in coupled models is you have to cover enormous range of scale. So in somewhere like Australia, you know, obviously, or anywhere in the world, you've got the animals happening on to the meter scale in their interactions, but the physics end of the world is happening potentially at basin scales. Now why would you need all of those things in a model that even if you're just thinking about how to manage a single reef in Australia, for instance? That's because the shelf properties, the actual thing that's happening on the reef, it spans like, you know, what, 10 orders of magnitude, 12 orders of magnitude there, from the small scale fish interactions up to how the reef system itself is physically affected. But even the management guys, the guys who have to decide if they're closing a reef or putting in a fish minimum size limit so you don't catch too many small fish, the area that they've got to worry about covers 2 to 3 orders of magnitude. So that's why so many scales end up in these big coupled or even small coupled models, because there's so many scales involved in the day-to-day processes that are happening. So those coupling things can happen sort of inside the model, so they don't explicitly look like they're coupled, but it's actually the same thought processes that have to happen. So for instance, there's lots of different ways of modelling the world. If we think about bringing humans into it, ideally you need social, economic, and biophysical, whether it's a simple qualitative model, a model sort of intermediate complexity to play with, a model that focuses only on one sector, like a fisheries model, or these more complicated models that start to shuttle ideas around where you actually do have feedbacks amongst more of the system. So you've got to think about which ones to include, what sources of delay do you have, and then ultimately what kind of coupling you want. So originally, pretty much every model in the world has started by coupling in one direction because that's easy. But a lot of the feedback, a lot of the critical behaviour that happens only turns up when you get the two-way coupling. And that's as computing power and skill and human ingenuity is moving forward, we're getting more and more of that happening. So that's the part that I'll try to focus on. So if we think about the whole of a marine system, these are all the different parts that we have to actually think about whether we need to couple them together and then how we do that. So if we just go on a brief tour of Beth's career, when I first started as a baby modeler, the physics end of the world didn't talk to the fish end of the world, they were separate. And people would say, well, that's not good enough. We probably need to have more than just phytoplankton in a physical model, so that adds zooplankton. And the fish guys would go, well, fish might need to eat something or live on something, so they'll add one more group there. And then I came along and said, well, my supervisor suggested I should say, right, what happens if we tied everything together and we get different fisheries questions? Ironically, I never got around to answering that question. I got so sidetracked with how you tied everything together. Since that time, over the last 15 years, there's been lots of different ways about tying these things together. You can either have the same degree of detail the whole way through, you can focus in the middle and sort of just paint in the things at either end. You can use the rhomboid approach and go for a lot of detail at certain steps down the chain but have thin links between them. But what's happening more and more is these hybrid models at the other end, where you use the best way of representing each part of the system and then figure out how to get those different things to talk together in a big Franken model, so that it's all bolted together. Now, one way you can do that is to have like a translator sitting in the middle. So if you think about the UN, the whole thing would collapse if there wasn't those people who could speak as fast as they can think in a different language. So the language is coming in one ear and say French and coming out their mouth in English. The UN couldn't communicate in the General Assembly without that translator happening. The same thing can be used to couple models together. So you don't have to have the overhead of trying to take Laurent's model and say, look, you have to have my equations coded in, or you have to do things the way I do, or vice versa. We can have a translator sit in the middle who knows how to speak the two languages. So information comes out of Atlantis, gets translated into French by the broker, and gets passed to Laurent's physical model, for instance. Well, it wouldn't be French, it would be what, the C4 trader, what he did over there. One of the complicating factors in doing that is think about how you handle space. Because the models have grown up differently, they won't handle space and time in the same way. So two of the most common ways of treating space are, the most common way is just to do a homogeneous grid everywhere. The other way is to try and break up the world, not to think necessarily in a regular grid, but to try to match the detail of the grid to where the detail of the action happens. I wasn't smart, I didn't think this up because I'm some kind of super genius. It was because when I started modelling, we couldn't fit the area I wanted literally as a matrix onto the size of the computer chip. It was too big. We'd have to keep swapping things in and out, it would be too slow. So I had to think about how to reduce the size of that matrix by having less boxes. So I sat down and thought about when you're sampling data, or actually when you look at an animal's behaviour or the physical properties like fronts, they happen in very concentrated areas, and other areas are quite, you can get away with a simpler characterization. And that's what led to this kind of box model approach that I use, but it was actually commonly used a lot more by the broader community back then. The physics guys have been better than ecologists at getting super big computers, so they've been able to go over to using this. The ecologists still do this sort of small computers. But regardless of how you model it, you have to be aware of the kind of artifacts that can chuck up. So this is an example from a big global model, and you can see with the red bits, that's where the estimated sea surface temperature was wrong. It was basically as much as 6 degrees wrong. The reason behind that was that the resolution and the kinds of physics they had in upwelling zones, where the physical properties changed quite rapidly and other processes are dominating, didn't match what was actually happening in reality. So one way to solve that was to use a finer grid, for instance, and bring in slightly different formulations. So in Australia, for instance, we went from a prediction that was really quite smooth and smeared to one that captured all the eddies that actually drive production. So you can imagine that if you're a fisheries manager trying to make decisions, you'd actually make very different decisions, particularly along the coast of eastern Australia, around here, based on whether you're using this smooth model or this model with eddies. And tuners love to sit on the edge. Tropical tuners in Australia sit there, and the southern tuner sits there. So if you've got your management and you're basing it, trying to be proactive and put management, spatial management in place, and you put it here, and they're actually all up here, you're going to have caused yourself a problem. When they adjusted the physics though, you can see that the biases aren't all gone, but it solved quite a lot of the problem. And there's a few different ways that that can be done. So for instance, you don't have to use a regular grid everywhere. You can even on those big climate models sort of zoom in and out as you need. Or you can go a different way and say actually in those zones where it's processes on a different scale that are driving the system, zoom your scale down by embedding a fine scale mesh inside that big grid. On the temporal resolution front, most models that we would think of, like what we're doing in NetLogo, everything in the model steps together on a constant path. Everybody has the same sense of time. There is a little bit of a trick in ecology where animals that grow slowly will do one big step, and animals that grow fast will do lots of little steps to add it up to that one big step and then go to the next one. The reason they do that is just for numerical stability. So you have plankton that go very fast and fish that go once. You don't want to calculate fish on a second time scale, it takes everything too long and they don't really act that way. But some of the plankton, you have a couple of minutes or a couple of hours for a plankton can be a long time. The other way to do it though is, what you've heard me talk about a little already, is you don't use the same time step for everything. So the bottom one is the kind of time steps I use in a model that's agent based, where the action of the animal or the agent dictates its time step. So for instance, a regional economy will go off once every 6 months, a fishing boat will make its decisions on a daily basis, and a fish will make its decisions on a minute by minute basis while it's awake. but longer times when it's asleep, or teenagers will spend 12 hours asleep, so you might as well save yourself some computational time by not ticking them. But then if they're running away from the police, then they want a faster timestamp so they can plan the chase. You do need an underlying heartbeat though, so things don't end up too far apart. We're just playing with science fiction because half the animals are in the future. When you start to be able to deal with those kind of scale problems though, you can start to really couple things together. So sometimes that coupling is by putting it all together in the same model and having the translation happen in that one piece of software. Other times you tie the software together. So this is an example of where temperature has been tied to phytoplankton in a nutrient field, so that you can see the evolution of all things together. And most of you would actually be quite aware of that, but you can take that process much higher up the trophic chain. So a French group has actually done this, where they had a climate model, drive a primary production model, drive a feed layer, so they didn't actually species resolve the feed, it was a size-based model, a different model again. Then they had a larval advection model, so a different model again. And finally they had the adult tube, so they actually coupled this whole chain of models together with feedbacks to be able to cover that in what's in that big global span simulation of the tube. Just like you've got your physical and your temporal constraints on the resolutions and the processes, you've got to think about the same is true for any living part of the system. So we heard earlier in the week about some of the ways that you have to think about when you're putting your trophic web together. When do you need to split the animals apart? When do you need to resolve the animals, and when do you lump them together? There's actually a whole bunch of rules about when it works and when it doesn't work. So that's something we're quite comfortable with now, just like we are on the physics side. And you're aware of the vampires innovation. Ultimately, regardless of how you're putting your models together in space or time or processes, you need to allow for alternative stable states. One of the biggest mistakes is to over-hardwire your model, to lock in behaviours that you've seen that must be there. One of the best tests of a good model is to see if it can produce that behaviour rather than requiring the behaviour. Because then you have a test to see whether you may actually have the process-based model. So they've been now doing this to tie ecosystem models in the whole big whole food web sense. The global climate models, for instance in the United States, they take the climate model, they've got an embedded hydrodynamics ROMS model. Inside that hydrodynamics ROMS model, they've now linked in